Okay, good morning everybody. I hope everyone's having a wonderful day. So before anything, I just also want to mention that your final assignment, that deadline is coming up. So hopefully you've been working away on your assignment. If not, I do check my email over the weekend. So just make sure you keep an eye on your work for that. How's everybody doing with that? Is everybody generally, how many people have finished the last assignment? Half done. Oh, good. We got some there. We got some that are done. That's wonderful to hear. That's wonderful to hear. Yes. Wonderful. So that being said, as you may, I already talked about this previous class. Why don't we talk about where we were last day? So last day I was introducing you to a more formal aspect of what we talked about earlier on the course, this idea called the reduction. So I just want to remind you what that is, because it's going to play a very important role in this lecture. So suppose I give you two problems. I call one of them pi 1 and the other one pi 2. I want to imagine having some way I can connect pi 1 and pi 2 together so that if I were to give you some algorithm that solves pi 2, that there's some way I can solve pi 1 using it. So the way that's very natural for this is this idea of a reduction. So this reduction here, this box here that I have an F here, that function or algorithm, its job is just to convert or construct an instance of problem pi 2 from pi 1. So you could think of it like I'm taking what's pi 1 and translating it into the word or language or whatever you'd like to call it that looks like pi 2, and then I tried to use an algorithm for pi 2 to solve pi 1. And the way a reduction works is that when I get a solution for pi 2, that there's either a very quick way for me to make it look the same as an answer for pi 1, or that they literally are the same. That's why I use same in quotation marks here. So this idea is a very broad one, but you're going to notice I'm going to narrow it down quite a bit in this lecture. So when I say same, will very often be the case is that when I tell you that if I give you a question that answers yes or no, what it's going to do is it's going to spit out an answer that's yes or no here. And that yes or no will correspond, if that was a yes answer for this one, it'll be a yes answer that spits out of here. If it's a no answer over here, it'll spit out a no answer here. So that's going to be the core part of a reduction for our lecture here today. So I want to talk about some consequences that come out of the idea of a reduction. So because I told you that this reduction gives you a way to translate instances of pi 1 into pi 2, imagine that I told you that there's a really fast algorithm for pi 2. This should remind you a little bit of what we talked about when we talked about lower bounds, right? The whole idea was I use contradiction to say, hey, look, what if I have this really fast algorithm for pi, in our case it would be pi 2 here. And then I tried to yield a contradiction that way. So one consequence of this is that if you have a really fast algorithm for pi 2, and I've translated it into terms of pi 2, that you could say that pi 1 is at least as easy as pi 2, because when I get answers out of pi 2 for my instance for pi 1, and if they're the same, then most certainly if I had a fast algorithm for this, you could see how you could use what I just described here on the board using this reduction to solve pi 1, right? So you can think of this like a little translation program that's going to take what you had over here and turn it into something that I could give to this algorithm for pi 2. So we're going to be interested later on in these reductions being efficient. So we want to make sure they run in polynomial time, but that'll be later, okay? I'll talk more about that in a bit. So on the other hand, you can also look at this in a different way. So you know that pi 2 is at least as hard as pi 1. So you might ask, why is that the case? Well, imagine this box here. So imagine I give you this box and I tell you, okay, there's pi 1 right there. So imagine I told you that, oh yeah, pi 2 was supposedly easier than pi 1. Well, I could present you this box right here and say, okay, well, if pi 2 is easier than pi 1, then you could simply build this reduction that turns it into something that looks like pi 2, and it spits out the same answer. Well, that would be a contradiction, right? Because now I just showed you a way to solve it. And it would be at least as easy as this. So in our idea, when we use our reductions, the whole idea is I want to make this reduction efficient. And whatever I'm doing to talk about it being the same is efficient. But we're going to really only care about really what's happening here and how it relates with pi 1 and pi 2 for this lecture. So another interesting consequence of these two things I just mentioned is if I have one of these reductions where I say pi 1 reduces the pi 2, I must stress that it's very easy to get the 2 backwards here. So it's going to be very common when you're thinking about this that you get the idea backwards. And this happens to everybody. It happens to me. It happens to a lot of people. So when you're studying this kind of topic of these reductions, it's very common to get it backwards. So just be careful. So if I have this reduction, so remember pi 1 reduces the pi 2, that's what this picture is. And if I tell you pi 2 is solvable, then pi 1 has to also be solvable. That's because if you look at my picture, if there's this reduction here, that's what pi 1 reduces the pi 2 means, is it has this reduction, and when I spit out answers from this thing, you could treat it like a black box. When I get answers out of this, they're going to be the same. So there's going to be some direct connection between these two problems. Some people call it a correspondence. So you have that, but on the other side, one of the more stranger things is if I told you that some problem was unsolvable, and you know that pi 1 was unsolvable, then you know you can't solve pi 2. It's by the exact same reasoning I gave before. So imagine if there was a way, then you'd present this box and you'd say, hey, look, that's really why you can't solve pi 2, because it would give you some way to solve pi 1, and if I told you pi 1 is unsolvable, then you can't solve pi 2, right? Otherwise it would lead you to an answer for pi 1 if this reduction exists. Like I said, these are really out there ideas, right? Like this is pretty abstract stuff, but it's also fairly concrete if you think about it in another way. Just remember this reduction, like I said, think about it as a way to transform that problem instance I have over there, x, into something we call f of x that will be, in fact, something I could feed to an algorithm for the other problem. And the important property that we have is that the answers are going to be the same. Okay? So does everybody have a general flavor for this box here? So if you're not sure really, just think about it in terms of programming. You can also think of this like some interpreter that's going to say, hey, look, I don't know what your problem over there is really in terms of my problem, this pi 2 here, so I'm going to translate it into one that makes sense for pi 2, okay? So often these involve sometimes complicated, but otherwise very elegant constructions that lead you to really nice connections between problems. And these connections between problems help us understand if a problem is easy or hard to solve. So on that, I want to focus directly in on the kinds of problems we're going to be interested in for the next couple lectures, at least for this part of the course. So we're going to be interested in what we call decision problems. And I must stress that many problems that you know and things that we've encountered in this course can be cast as decision problems. So these are problems that can be formed as instances with either yes or no answers. So it sounds rather straightforward, right? So if you take a decision problem, if we're studying two decision problems, and I tell you that the answer is the same now, do you see now that if I were studying two decision problems, if I tell you that the output of this is the same as the solution for x, you can most certainly see that, okay, if the answer is yes over here, it most certainly has to be that the yes answer is also over here, right? And if I have a no answer that comes out of here, it most certainly has to be the case that the answer is no over here. Does everybody see that? So very often when I talk about decision problems, there's going to be what I'm going to call yes instances. Those are the ones which the answer to the solution is going to be a yes. And there's going to be what I call no instances. These are the ones for which they're going to have no answers for their solution. So is that clear, everybody? So I want to do an example with you just to illustrate. So you can think about this like if you thought about the problems as having some Boolean value. So it's like when we do like a test, the check, for example, when we did earlier on in the course, I asked you about if I wanted to know if an array had all the unique elements in it, or if there's any duplicates. These are examples of ones that have yes and no answers, right? Does this array have a duplicate in it? Does the array have all unique elements? These have answers that are yes or no, right? But here's another example just to illustrate the difference between the two. So we studied earlier on in the course what we called the minimum spanning tree problem, right? This is actually an example of what we call an optimization problem, right? We talked about that earlier on in the course. So if I were to write this out, I would tell you it's given a weighted connected graph, G is equal to VE. Compute a spanning tree. Compute a spanning tree with minimum total cost. So this is the minimum spanning tree problem. We've seen this one earlier on in the course. Now, this is an optimization problem. This is not a decision problem. However, there's a very natural way for me to talk about optimization problems as decision problems. And this is going to be very common when you're studying optimization problems and you want to say, okay, how does this fit into my weird framework where all of them are going to be decision problems? Because the theory of what we call intractability is very much built around this concept of a decision problem. Here's a way you could think about it. Actually, I have a question for you. Does anybody see how I can frame this as a yes or no question? That's very often how you cast decision problems. You can think about it like a question. You could pose it as a question. Does anybody have any ideas? Rather than me giving it to you, does anybody have any ideas of what I could frame? Like, if I were to ask you, okay, well, is there a natural way I could talk about this problem as a question? If I were to pose you a question. Now, the big part I really want you to try to avoid doing is try to avoid using the word minimum here. Instead of thinking about it as something that you could potentially use to optimize the spanning tree. So think about it as posing a... So that's a good point. That's a good place to start. Is there a spanning tree? That's a very good place to start. So why don't we start writing that? So here's the minimum spanning tree problem posed as a decision problem. So I could say this is given a weighted connected graph, right? We have a weighted connected graph. A weighted connected graph, G is equal to VE, just like we have over there. Now, I'm going to help everybody with one other suggestion I'm going to make, because we're almost there. I'm just going to add one small little detail in. I'm going to say, and an integer k, and an integer k. So I'm going to add in this parameter I'm going to call k. Now we're going to ask this question. Does G have a spanning tree with total cost at most k? So let me reiterate that. So given a weighted connected graph G is equal to VE and an integer K, does G have a spanning tree with total cost at most K? So now I have introduced this integer K, and now I'm asking you a question. Is there a spanning tree where is total weight or total cost, however you'd like to think about it, is at most K? So now it doesn't look exactly the same as this one, right? But it's quite related. I have a question for you. Does anybody see how I can use this problem to help me solve that problem? So what does this K have what's the relationship K has with this problem up here? So think about it. What would you like K to be? Yeah, you want it to be the smallest possible K you want. Yeah, exactly, everybody. Exactly. You're getting it. That's wonderful. So you want K to be as small as possible. So I have a question for you. If I were to give you this and I told you, hey, look, I can ask you a series of yes or no answers to this. Does anybody have any ideas of how I could solve that problem? If I were to compute a spanning tree whose total cost is at most K, and I told you yes or no, can you tell me how I would compute the minimum spanning tree? So one suggestion is using recursion, but what algorithm would you use? So I'll give you a hint. When I have K here, you could think about this like the true value of the optimum is somewhere. So say, for example, I start off with 0 and I have 1, 2, 3, 4, 5, all the way up to the number of vertices. And suppose that the optimum was, say, right here. Say the optimum value right here was 3. And I have my guess that I'm making. You could think of K like a guess, even, in this context. If you imagine this like an array, you keep in mind you don't need the array, but it's a useful thing. You can think of this as a list of numbers. Do you know a search algorithm that you could use to figure out what this should give you if you ask this question to determine whether you consider it or don't consider it? So you can use linear search. You could start off at 0 and ask this question, right? You could do that each time. So is there one with cost at most K? Yes or no? Well, probably it's going to be no, right? So if you answer no, you go up 1, right? You keep doing this until you run into 3 here. That's one way of doing it, but there's something you could do a little better than that. Because first, that will work. That indeed works. Just notice that we're at the mercy of how many guesses we make here. It's actually linear in the number of vertices in my graph, right? That's the number of guesses I have to make. So I want you to think back to the recesses of your mind, to a search algorithm where you can make certain assumptions about what the array looks like. Notice that this, if you imagine this list of numbers like an array, keep in mind you don't actually need the array, you just need to know the fact that they are what somebody in analysis would call they're monotonic. They're always going to be, in our case, increasing. So think about it like I give you this K and I give you the graph. Can you find the best possible K? In this case, you want it K to be this one, using a small, at least number of steps you could think of. So we already know that if you start up over here on the left and you work your way to the right, you can get it. And that's akin to linear search, right? Or sequential search. But we have more information here. We know a better way of doing this, right? So remember, think of this like an array. What would you do? Binary search. That's exactly it. So now what you could do is you could actually use binary search. So you start your K somewhere in the middle here, and then if you get a yes answer, you know, okay, well, since this is a minimization problem, that means you're going to then cleave off and remove, you're not going to consider what's off to the right because you already have something, right? So you know that your guess, the better guess might actually be smaller. So you discard the larger half and then you work with the smaller bit. And you can keep repeating this process until you find the smallest possible k such that you get a no answer. So you just hang on to the best answer you have so far. This is actually a very common paradigm that we use to talk about the connection between optimization problems and decision problems. So very often when people study optimization problems, they call this the decision variant of the optimization problem. And if you ask questions about this, what it means is that this problem is at least as hard as this problem, because all you have to do is you just simply use a binary search process, repeatedly making guesses, and then that'll get you your optimal value. So you'll see very often I'm just going to pretend that this isn't a thing and I'm just going to proceed with this. Is that okay with everybody? So you're going to find very often I'm going to phrase my questions as yes or no answers as opposed to saying I'm going to compute the optimal one. This is just the framework that a lot of these theoreticians that think about these things like to talk about them. Are we all okay with this? So give me a thumbs up if we're all good to go. Okay, great. So let's proceed over there. Now, I'm going to take a little trip off to the side, and I just want to mention that using this idea of a decision problem, there do exist decision problems that actually aren't solvable by any computer algorithm. Like there is no algorithm that you're going to be able to find under the complexity theoretic assumptions that people make about the fundamentals of computer science, which is very strange to hear. Usually people think, yeah, I can write a computer program and that means that there's always going to be some way I could solve some problem. Unfortunately, there is an actual ceiling on how many what problems you can or can't solve. This is a lot of the very fundamentals or foundations of computer science are built on from say, about the early mid 20th century. A lot of people will say, yeah, modern computer science started then. So I want to mention an unsolvable problem to you. And here's the neat thing. If you use the framework of a reduction, if I were to present an unsolvable problem to you, you can actually derive more unsolvable problems if you give me one of these reductions. I'll be doing some examples of reductions in a bit. This is more of a sidetrack that I just want to show you just an example of something that there is no algorithm that we think even exists for this under certain assumptions that are typically seen as very reasonable. They're the same theoretical underpinnings, by the way, that underpin the same models that we use for our analysis in this class. But I won't go into that too much here. So consider the following problem. So this is going to be a decision problem I'm going to pose to you. So here's input. So here's going to be the input for this problem. This is going to be an arbitrary computer program. Say this is something that you wrote up in something like C++. Let's give it a name. We'll call it also, it's going to be named C. It's just the name I'm going to give it. And it's given in some programming language. I'm just picking C++ just because it makes it more fun. And suppose this program takes as input W. So you can think of this just like you had your typical program and it gets, say, even from the command line, or it has some inputs it takes in. This is what W is going to be for our program. So the output for this problem is does C terminate on input W? In fancy terms, people like to call this halting. Does it halt? So if you give somebody an arbitrary program, now I'm not saying a specific program, but I'm saying an arbitrary program. So like this can be any program somebody could possibly throw at you. And your job is to design an algorithm that could tell you that that arbitrary program terminates. And the answer would either be yes, it terminates, aka it halts, or it does not halt, meaning it doesn't terminate. That means it's going to run in an infinite loop, right? So you can think of this just like if I were to sit down and I told you, hey, look, you design me a computer program that will test if a program has an infinite loop in it. That's another way you could think about this. So this is what we refer to, so I'll call this, this is called the halting problem. You may or may not have heard of this from in the past. If not, that's okay. I know it's a rather popular problem that usually the media likes to cling on to when they talk about some of this kind of stuff. So Alan Turing in 1936 proved that this problem is unsolvable. Now, I must stress that there's a technical term that people use for decision problems that don't have algorithms for them that can decide yes or no. We call these undecidable. And now you might ask, Dan, why are you bringing this up? Is that, like I said earlier, you can use reductions. So if I give you something like the halting problem and you present a reduction that takes the halting problem and it shows you that you can actually, using via reduction, translate it into a different problem, you could show that that problem is also unsolvable, which is kind of wild, right? Now, if you're curious more about this and the theory that pins this down, a course to take for this one is CS411. So if you want to learn more about these limits of computation, CS411, they build up right from the beginning. They start off with very simple models of computation all the way up to things like our RAM model and the Turing machine model, which is the one that Alan Turing's ideas were based off. Now, Turing didn't call it the Turing machine, but he called them automatic machines. But you see in that class how you use reductions in this sense to show that there are these things we call undecidable problems. So I just felt like mentioning that. So reductions are very useful in this sense too. But what we're going to be focusing, first, are there any questions about this? This is a very interesting result in its own right. It's fundamental. Like Turing, there's an interesting story all behind this one. But it very much is closely related to a lot of 20th century mathematics that stemmed from 19th century mathematics and questions around infinite sets and what infinity means and strange paradoxes that come out of these kind of things. It's a very, very deep subject, what we call computability theory. It's like the bedrock of computer science. So like when Turing, one of the pioneers of what we would call computer science today, when he was working on a lot of this stuff, they didn't have what we call computer science. In fact, computers were like this archaic thing in those days. The idea of a computer was still in its like infancy. So Turing was talking about these limits of computation even before you had a general purpose computer, okay? So that should give you an idea of just how deep a lot of this theory that I've been showing you goes deep into. Like it goes really far in. So, and I must stress that there is infinitely many of these unsolvable problems. This isn't just an outlier. Like there's a lot of them. So many I can't count them for you. Now, what I want to do today is we're going to be interested. So that's the end of that point. So if you're interested in this, take 411. We start up right at the beginning where you start off with very simple, like finite state machines, and we work our way all the way up to these Turing machine-based models that you can address questions like this one and use reductions in this sense. So we will be interested in what we call polynomial time reductions. So what does that mean in plain language? That the f I defined over there, so it says f must run in polynomial time. Now one thing that is sort of an implicit assumption I'm making when I say this is that it's always with respect to the input size, just like we have always. So that also means implicitly that the size of the instance that you're looking at for, when you feed that over to the algorithm for pi2, its size also has to be polynomial in the size of the original instance. That's implicit in this definition. So is everybody okay with that? So I'm just going to give you a fancy name whenever we have a reduction that does this. So we rewrite pi1 reduces to pi2, but we have a special p here. What this is going to represent is going to mean, or say, pi1 polynomially, it's a fun word for Friday, polynomially reduces to pi2. Whoops, that's a quotation mark, not a parentheses. So what I'm going to assume at this stage is I'm going to give you two decision problems, and I'm going to ask you questions about, okay, does there exist one of these reductions where that reduction, that algorithm, is always going to run in polynomial time with respect to the input size? And we give it a fancy name. It's this inequality with a p here. If people don't put a p there, that's usually just meaning that they aren't bounding the running time by a polynomial usually. There's different kinds of reductions in complexity theory, but this is one of the standard ones. So does everybody understand the game plan? So I'm going to present you some way that we're going to do one of these reductions where every time I get a yes answer, I'm always going to get a yes answer for my original problem. And whenever I have a no answer, I'm going to get a no answer for the original problem I look at. And the algorithm I'm going to use to translate the problem from one language of talking about that problem to the other has to run in polynomial time. So does everybody get the general idea before we proceed to our example? Just want to make sure everybody's got the game plan in mind. Are we good to go? Like I said, we're seeing a lot of interesting stuff today. So let's do an example of one of these polynomial time reductions. You're going to see that these reductions, they give you ways to talk about different problems, almost like, say, a zoologist would talk about different species of animals. And that's very much how a lot of complexity theorists look at problems. They'll just say, okay, this problem's like that problem, we just put this one wrinkle on it. And it's very often what happens is that I'm going to tell you how I could take one problem and speak about it in terms of another problem, but it inherits all of the properties of that original problem from an intractability standpoint if we have one of these reductions. So when I mean intractable, for example, if I know my original problem it does not have efficient algorithms for it, I'm going to give a very special name for some problems that are like this. Then if I do the reduction, I'm going to end up with another problem that also has to be intractable. The other way also is also true. So suppose I give you some pi1, and I don't know an algorithm for that one. What I could do is if I have this reduction, I could give it to this other problem, which I do have an efficient algorithm for. I'd perform the reduction, and I could get an answer for the original problem that I was interested in. So, like I said, you can think of it like I'm translating the problem into another one. Another way you can look at this, and this is one that's very useful when you're studying complexity theory, is you could view it like I'm taking one problem and I'm showing you that the other problem really just is the same problem, but it's like a special case of it. It's not that they're equivalent, it's just that one is a special case of the other, it's just in a different language. So I just want to draw you one picture just to get you the idea of what our reduction will look like. So when I talk about a decision problem, so here's pi 1, and here's pi 2. Sorry, that's a 2 up here. Let me fix that. So I have pi 2 here. If I look at all of the problem instances of pi 1, there's going to be those that I call yes instances earlier, and those that are no instances. In pi 2, there's also going to be yes instances, and there's also going to be no instances. Remember, these are decision problems. Either the answer is yes or no, okay? So does everybody see why there's only these two buckets that I'm going to have the instances? Remember at the beginning of the course how I talked about a problem being a set of or a class of instances? And each one of those dots would be something I try to solve with my algorithm, right? So it's going to be no different here. Now, I know the answer to some of them is going to be yes, and the others are all going to be no. From a complexity theorist standpoint, there's also ones that may make absolutely no sense with respect to the problem. They may sit out here, but they represent a whole bunch of garbage. They may represent encodings of instances that just simply don't make any sense with confines of the problem. In this course, we won't worry about those. In a class like 411, you would. So when I have these yes and no answers, so I consider any one instance in here, I want it so that this reduction will take all the instances that are the yes ones, and it turns them into what's going to be a yes instance for pi 2. All the ones that are no answers, I would like to turn these into instances that are no instances for pi 2. Now, I must stress the way I drew this. So what I'm saying is that if I give you an instance here, I want to convert it into an instance that's going to sit in this circle. And that's what F's job is to do. Just like if there's a no instance, F's job is to turn it into an instance that is a no instance, like this. So, does everybody understand the game plan? So this is why I also mentioned that you could think of this as a special case of that problem, because notice that I use a smaller circle. I didn't show that every single one of these has a corresponding instance in pi 2. I said that there is actually, for every one of these, there's some instance in pi 2 that it translates into. Very often when you make these reductions, you like to make it so that the instances over here are some subset of them that you know things about them. That's very often the trickery that the people that are interested in these kind of reductions like to use. Okay, so let's do our example. Let's proceed. So I'm going to consider two decision problems here. And since we've talked about graph theory, I can talk about these now. So the first one I'm going to consider is what we're going to call the Hamiltonian cycle problem. I'll abbreviate it as HC. And it works like this. So given an undirected graph, G is equal to VE, does G contain a Hamiltonian cycle? I'm going to define what that means in a moment. Note, a Hamiltonian cycle is a simple cycle, that contains every vertex V in V. So let me draw you a picture of what one of these would look like. So suppose I give you this graph. I just think about how I want to design this graph. Let's do it like this, and I'm going to number them just to make it a little easier for us to talk about it. 0, 1, 2, we'll call that one 4. We'll change it to 4. So I have them numbered from 0 to 4. So you might ask, Dan, does this graph have what we call a Hamiltonian cycle? So a Hamiltonian cycle, remember, it has to go through this entire graph, and it's simple. So that means it does not repeat a single vertex twice. So remember our definition of a simple cycle earlier on? So we require that this cycle contains all the vertices. So does anybody see a good simple cycle for me to use that is a Hamiltonian cycle? Just tell me the order we visit the vertices in the chat. I will tell you up front that this does have a Hamiltonian cycle in it. I must stress there may be more than one. Yeah, let's see. 0. Yeah, I got a good one in the chat. Let me just, here, I'll use a different marker to draw it out. So I see 0. So I see 0 to 3, 3 to 4, 4 to 1, and then I have 1 to 2, and then I come right back to 0 here from 2. So this is an example of a Hamiltonian cycle. Some people call this a Hamiltonian circuit. It's just another graph theoretic term that means the same thing as a simple cycle. So that's what a Hamiltonian cycle is. And I'm asking, if I give you this graph, does it have one of these? I'll tell you up front, this problem is not easy. The best known algorithms we know for solving this take exponential time. That doesn't mean it does not exist. It just means that we don't have one. And like I said in a previous lecture, I would like to have some way of talking about difficulty of solving problems in a way such that you could convince, say, your boss, your supervisor, or somebody to say, hey, look, this problem is actually really tough, but nobody knows how to solve it efficiently. So I'm trying to give you a framework to talk about it like this. So that's one problem. The other problem I'm going to consider is what we're going to call the decision version. The decision version of what we're going to call the traveling salesman problem. Now, you may have heard of this problem before. It's a very famous optimization problem. I'll tell you straight up that there's people that in my area just study this problem. Like, it's just, that's all they study are versions of this problem. I'll abbreviate it as TSP decision like this with a hyphen, DEC. It's just the name I'm giving it. So I must stress the traveling salesman problem, as originally cast, is an optimization problem. And by the same reasoning that I gave you for our minimum spanning tree example, you can, if you solve this one efficiently, you can always compute the optimal value of a TSP tour, which I'm going to define in a moment, in polynomial time, if I gave you an efficient algorithm for this one that runs in polynomial time. So here's how this one's going to be cast. It's a given a weighted complete undirected graph. Now remember, complete means that for every vertex in the graph, each vertex adjacent to every other vertex. I must stress that there's some versions of the traveling salesman problem where they do not define it like this, but there are equivalent ways of transforming it so it looks like this. So I must stress that. So some people like to talk about it a slightly different way. This is just going to be helpful for us. I'm going to call it H, and I'll call its vertices N and its edges F, and an integer K. Usually you can define the K to be between 0 and the number of vertices, or in our case, this K will play a different role. Instead, it will be that it's based on the weights of the edges. It'll be like, at least, it can't be no more than the sum of all the edge weights. But we're just going to call it integer K. Is there a simple cycle? Is there a simple cycle in G that has every vertex in V? So when we talk about it in the terms of this problem, we call that a TSP tour. Called a TSP tour. I'll put that in parentheses. Called a TSP tour. So that its sum of weights on edges is at most k. So suppose I gave you a graph that's going to be weighted and complete, and it has some integer k. Oh, thank you. Thank you. It's h. Very good. Thank you. Yeah. So when I say h there, that's the name I gave the graph. Thank you. So notice that this definition for my TSP tour, it should look like something I just wrote above. Can somebody tell me what a TSP tour actually is? Well, TSP tour is, in fact, a Hamiltonian cycle. Does everybody see that? Because it has to contain every vertex into the simple cycle. So it's a Hamiltonian cycle. What this problem is asking about is, given a graph, can you tell me that if there's a Hamiltonian cycle where I add up the edge weights along that cycle if it's at most k? As its optimization cousin, you could think of this like, I want to find the Hamiltonian cycle with the least total weight. Or you can think of this as a least length TSP tour or shortest TSP tour. So I'm going to quickly jot down the reduction that you would use. I'm going to put more details in the notes if you're curious about how you would prove it. But I want to show you how you'd get the reduction here. And believe it or not, this one's actually not that bad. It's actually quite simple. Hence why I'm going to quickly finish it up for you. So anyways, let's move over a little bit. There we go. There we go. Okay, wonderful. So I'm going to say below describes. So if I have Hamiltonian's cycle, I'm going to show you a polynomial time reduction from Hamiltonian cycle to this decision version of TSP. I must stress that you can make it so it runs in quadratic time. So it will indeed run in polynomial time. So I'm just going to tell you given a Hamiltonian cycle instance, we have graph G is equal to VE. And I must stress that when I use n, it's always going to be that n is going to be the number of vertices for G. It's going to be important in our reduction. So we build. So remember, my game plan is I'm going to use this reduction to translate the Hamiltonian's cycle instance into one that looks like the traveling salesman problem instance, okay? Yes, yeah, next time we're going to talk a little bit more about this. But do take a look at this. It's just going to be very quick. So we build in polytime, so polynomial time, a weighted complete graph. Weighted complete graph. H is equal to NF as follows. as follows. So I'm going to start off that F is going to be empty. So I'm going to start adding edges into F. So here's how I'm going to do this. I'm going to let the vertices of H be equal to V. We want them to be the same vertices. Then what you do is you take each pair of vertices in G. Then for each pair UV. So you just take each one of the pairs of the vertices of G. So if there's an edge, UV in G, you're just going to add edge UV to F with weight 1. So if the edge is present in the original graph, you're just going to add that edge into the graph and you're going to assign its weight to be 1. However, it could be that I have a pair of vertices and there isn't actually an edge in my graph G. That's the other possibility. So if that doesn't exist, you're just going to add an edge. You're going to add an edge into H called UV. And its weight is going to have weight 2. And then lastly, you're just going to assign K, because remember, K is also involved with this problem. You're going to assign K to be equal to N. So if you think about these instances, every one of them is going to now look like this graph that I've just described here. So remember in my reduction, I had it where I take the yes instances or no instances and I translate them into something that looks like the other problem. So this is one way to do it. So now I have a weighted complete graph and now it has edge weights assigned to it for one case. Then the other case I have 1 or 2, depending on if it's present in the graph or not present in the graph. And I'll show you an example next class, but here's the theorem that connects the two. Here's the theorem that you use to connect these two. So the theorem is just this. There is a Hamiltonian cycle in G if and only if H has a TSP tor with total length at most n. So what this theorem tells you is that when I build this H, remember, this is some instance of the decision version of the traveling salesman problem. When I get that particular H, I want some theorem that connects H to G. And this is the natural theorem that you get, is that if there's a Hamiltonian cycle, then there's going to be a TSP tor and its length is going to be at most n. I want you to think about, for next time, what exactly that Hamiltonian cycle looks like in H. So we'll come back to this next time. I apologize for going a little longer here. When we come back, we'll talk about this, and I'm going to define a couple of interesting complexity classes, and then I'll leave it off to talking about what the grand picture when it comes to this theory of intractability goes to, okay? So that being said, I want to say thank you very much, and have a good weekend, everybody, okay? So I'll see everybody later.